picking up on that thread, our next panel is literally about the science. And so we're going to have 3 of the world's best scientists come to the stage and give a 10-minute TED Talk style presentation on a subject that'll help expand our knowledge as a group. That's the whole goal of Forecast, as I was mentioning at the beginning. And then after those TED Talks, they're going to sit down and have a panel discussion that we can then learn more about the science and the actual facts of what we can and cannot measure today. So this next session is called Challenges and Innovations, the State of the Art of Climate Science and Modeling. And to kick off this session, I'm going to introduce the moderator of the panel, who will then come and sit down with the other panelists and introduce them, and then we'll get into the session. So I'd like to introduce Amanda McCarty, who is the director of NOAA's Climate Ready Nation Initiative, where she leads the efforts to enhance NOAA's ability to provide products and services that support informed climate action. Amanda just returned from NOAA after 3 years as a senior advisor in the Office of the Special President Envoy for Climate, working with none other than Secretary Kerry. Please join me in welcoming Amanda and her panelists to the stage.
All right, hello everybody. Matt, thank you so much for the introduction. I'm now going to introduce you to the rest of our esteemed panel. First, Dr. Kerry Emanuel. He's the Cecil and Ida Green Emeritus Professor of Atmospheric Science at MIT. He's a specialist in hurricane physics and was the first to study how climate change affects hurricanes. He has authored over 200 peer-reviewed papers and 3 books, including Divine Wind, The History and Science of Hurricanes, and What We Know About Climate Change. Dr. Gavin Schmid, at my left, is the director of NASA's Goddard Institute for Space Studies here in New York. He served as the acting senior climate advisor to the NASA administrator, and he focuses on climate simulation across past, present, and future scenarios. And then down on the end, we have Dr. Edward Kearns, who's the Chief Science Officer here at First Street. He also serves as a special government employee on a federal advisory committee to the U.S. Treasury, advising the Financial Stability Oversight Council, and is a member of NASA's Applied Sciences Advisory Board. All right, so for the first part of this session, each speaker is going to give a short presentation on the specialties that they have in climate science, specifically geared towards what you all need to understand when thinking about climate risk and how the climate is changing. So Gavin, you're up first.
Okay. Hi, thank you very much for having me. Okay, go. I'm going to talk about how we understand climate change, how we know what it is that we know and what it is that we can predict. We know that the last 2 years have been exceptional, both in terms of the statistics of climate change, but also the impacts. And you're mostly here because of the impacts, and the impacts are now so far outside of the noise that people are demanding that we explain them to you. The changes that we've seen have been about 1.5 degrees Celsius above the level of the pre-industrial. Now, that seems like a very small number. The temperature in this room is fluctuating by about that as we're sitting here and producing heat out of the top of our heads. But it's about halfway to the Pliocene. Right? The Pliocene was the last time that carbon dioxide was this high, and it was a planet that you would not recognize. Sea levels were 25 meters higher than they are now, and the forests went all the way up to the Arctic Circle, and Greenland effectively did not exist as an ice sheet. The changes that we've seen, there is some uncertainty back in the 19th century, but it doesn't matter how you put this data together, it always gives you the same trends that we're seeing right now. And these trends are large enough in the global mean to start having an impact on the local weather. How do we understand this? We use climate models. Climate models use inputs of things like where the mountains are, where the continents are, what kind of soil textures you have. Those things get updated on a regular basis. We combine that with physics, conservation of energy, conservation of momentum, the fluid dynamics equations, and parameterizations for things that we can't quite resolve a priori, like cloud processes, rain processes, soil moisture, and the like. We pull all those things together, we can tune those models, we can calibrate those models so that they look as much like the real world as is physically possible at this moment. We're using advanced machine learning techniques to do that now. And then we evaluate those models. And we find that in each generation, these models are getting better. They have fewer biases. They have become more complete. But there are still issues, and there are still targets to be improved. And so we go around again. Unfortunately for you as citizens, this is a growth opportunity for scientists. And we keep on doing this because we're never going to be done. The models are never going to be right, but they are increasingly useful. Let me give you an example of how we understand why the changes have happened over the last few hundred years. If you go from the top there, you're looking at the stratosphere. That's going to cool over time. Then you're looking at the mid-stratosphere. Then you're looking at the surface. And then you're looking at the ocean. So we're looking at the total column of the atmosphere, from the top of the atmosphere to the bottom of the ocean. And those time series that you can see, perhaps, just going out to the sun, there are 3 lines there. The green line is what happens only if natural processes occur. So that's volcanoes, the solar cycle, that kind of stuff. The red line is what happens when the human element is put in. The changes in greenhouse gases, the changes in deforestation, the changes in pollution, ozone depletion, all of those things come in. And then the white line is what happens when you put them all together. And then if you can see, well, the blue line is what happens when you put them all together. And the white lines are the observations. All of the trends in all of these different things, from the top of the atmosphere to the bottom of the ocean, from the tropics to the poles, all of those trends come from the human component. Without the human component, nothing would have happened, right? So when people ask us, how much of what's going on right now is because of us? The answer is all of it. And if you want to be super scientific, you can say plus or minus 10%. But the answer is all of it, right? And that has a profound implication for what the trends are going to be in the future, because we are in control of the trends in the future. The dominant uncertainty for what's going to happen next is what we do, right? We are in control of what's going to happen next. We have agency for what's going to happen next. And so while there is uncertainty because of the initial conditions, because of the weather, while there is uncertainty because of the structural biases in the models, the uncertainties in the models, the biggest uncertainty is what we are going to do. Those different levels that you can see there, they go from heroic levels of reduction of carbon dioxide to a burn-it-all scenario where literally we find all the hydrocarbons we can find and burn it all. That difference is the difference between a changed planet, for sure, or a radically changed planet. And I have a lot of preferences for which one I want to see. Where are we going now? People want higher resolution, more complexity, more details, right? The resolution of these climate models right now is around 50-kilometer boxes, right? So every grid on the Earth's surface is like a 50-kilometer box, right? So that's like from here to Princeton, maybe, right? There's one box, but there's a lot of variability there. People want smaller, more. They want more. But the problem with wanting more in terms of resolution is that every doubling of resolution is an order of magnitude more compute, right? So if I want to go from 50 kilometers down to 1 kilometer, right, that's like 5 doublings of resolution. That's 100,000 times more compute, right? Very hard to see where that's coming from. We have more and better observational constraints coming online. NASA has new satellites that are measuring things that we have never measured before that will go directly into these models. The ESA has a new satellite that just launched, EarthCare, which again is measuring things that we have never seen before. Those constraints, those new observations will reduce the uncertainty in climate modeling. But we still want to do more. We want to do more to calculate the changes because of the weather. We want to be able to resolve those tail events. We want to understand the uncertainty because of things that we don't understand. We want to look at the uncertainty because of the structural changes in the models. All of those things take more compute, and again, more compute. Machine learning could help, right? Machine learning gets us about 1 order of magnitude faster. Okay, but that's not sufficient. Downscaling helps because it kind of fills that gap between the resolved scale and the needed scale. We can do better in terms of the scenarios. I showed 4 scenarios. Obviously, the possibilities for the future are much broader than just 4 scenarios, right? We can use machine learning and emulators to fill out those gaps very effectively. But all of these things are going to cost. And it's not quite clear where that new compute is going to come from or how quickly we will be able to progress to meet these challenges. But our goals are very clear. We need to reduce bias in these models. We need to increase the completeness of these models and increase the coherence of these models. And we need to enhance the accessibility of the information that we are producing. We have in the databases that are publicly available and downloadable, but they're petabytes of data, and most people, and that includes many people in this room, are not able to access that data, despite the fact that it's publicly available, because we don't make an effort to make that accessible to people in ways that are useful to people. And so while reducing bias and increasing complexity are going to cost an enormous amount of extra computational expense, enhancing accessibility is something that we can be doing now. We have information. That information, for the most part, is not being used, and we can make it so that we can use that data to make better decisions. Thank you very much. Thank you.
Good morning. It's delightful to be here with all of you this morning. So my preoccupation over the last 20 years is how do we go from a general theme of climate that you've just heard from Gavin down to the whole question of quantifying risk, which is what we're all engaged in professionally. How do we go from climate to risk? And I'm going to tell you in my little 10 minutes about progress we've made along those lines. Let me begin with this graph. This is the global damage done by climate-related weather hazards, specifically storms, droughts, floods, and wildfires, normalized every year by the world domestic product. And you don't have to be a statistical wizard to see there's a very large upward trend in that, which is what concerns all of us. But let me point out that a lot of that trend is driven by population changes. People are systematically migrating from less dangerous to more dangerous places. It's not an accident. We in the United States and many other countries are paying them to do that, and that will be the subject of this afternoon's session. But it's woven in with what I want to talk to you about, which is the climate hazard component of that, because the change, the increase in the weather hazards is what the Defense Department would call a threat multiplier of this population-driven trend. So the two of them together are what's driving a curve like this. So 40 years ago, we began to understand from purely theoretical considerations that warming the climate would increase the intensity of hurricanes. This is pretty simple physics. Physics that I could explain to you if I had 10 minutes of your time. You don't really need an advanced degree to understand it. And in recent years, colleagues have been able to show, as you see in this graph, from satellite observations of actual hurricanes that their intensity is increasing as theory predicted they would. By the way, the theory is silent about the frequency of the storms, but the intensity is really important because most of the damage done by these storms is by the most intense events. So that really grabbed our attention. And what we find, the situation we find ourselves in today is fascinating and disturbing. Climate change is happening fast enough that it's basically invalidated a lot of the assessments of risk that you're all aware of that come from cat modeling industry and so forth, because, and this is the natural thing to do, there's nothing they did wrong, it's natural to base those in the first place on historical statistics of the hazard. The problem is that while most of the catastrophe models and other forms of risk assessment are based on historical records, in the first place, those records are too short for purpose. It's the 100-year events that really accumulate to give you a large annual average loss in many hazards. So even if the climate weren't changing, we'd have a problem. But the climate is changing, so much so as to pretty much invalidate the assessments of risk, which even today we're basing a lot of decisions on. And that's the fundamental problem that I see, and it's also very well described by Matt in his introduction this morning, was a driver of the First Street Foundation. So I argue, and I've been arguing for a while, that we can no longer rely on history as a guide to the present. Okay, I haven't talked about the future. Right now, what's the risk now? We don't have adequate information for that. We, in the scientific community, have to do a better job communicating and quantifying that risk. Let me just give you an example of where I think we're headed with this, and which really boils down to using all of the physics, to begin with the global climate models that Gavin so nicely described, downscaling of events that you can't resolve with today's climate models, like hurricanes and severe convective storms, but we're getting better at that. And starting to actually model business performance. Now, I'm going to show you a really naive example, all right? This is more of a cartoon than anything else, although it's actually calculated with real data. Supposing we have an insurance company that starts out with a certain capital, and it's a very boring company. It has fixed assets that don't change in value over all the place. It has fixed income from premiums, investments, and so forth, and fixed operating expenses. But the only thing that changes over time is its loss. In the first place, from the natural volatility of loss. And in the second place, although not on this particular slide, from climate change. All right? So let's say this business starts off with $500 billion in capital. All right? And we just let it run forward for 150 years. Steady income, steady expenses, steady difference between the two, but volatile losses. In a stable climate. We're not allowing for climate change now. So what you see on this graph is the probability at any one point in this graph of the amount of capital that that company possesses on the vertical axis as a function of time. So as you go forward, you have this envelope of probability. What you don't want to happen is to wind up unlucky in the low probability part that's below that white dashed line. That's when the board of directors of this company would consider the business to have failed, okay, if the capital drops below that. And so you see this is a pretty healthy business going forward. Again, it's a cartoon of a business, but we actually ran this model with those assumptions. And it's a profitable company. After 40 years or so, the probability of business failure is negligible. All right, so this is a well-designed firm. What happens if we now allow the climate to change in response to increasing CO2? And this is the next graph on here. Same exact conditions, but the climate's changing. Now, these losses, I should mention to you, are based upon downscaling hurricanes from climate models. Hundreds of thousands of these storms, many, many more than you could ever see in a historical database, but which have been compared very carefully to history where we have historical data so that we have some confidence in it. And you can see that not very long after the climate starts to change, the probability of business failure goes way up. This is not a healthy enterprise anymore, all right? So I think this is where we would like to head, obviously in a much more detail with all the assumptions that I mentioned to you. We'd like to start modeling businesses and how they would respond to climate change. Let me just conclude by saying that I think, and this emphasizes a point that Matt made earlier as well, that this kind of quantification of risk is exactly what people need, A, to make intelligent decisions about their own lives, about their assets and companies and governments as well. But it's also something that can finally motivate people to demand of their elected representatives, for example, that they do something about climate change if they know what the cost really will be, rather than just arm waving and say it's going to cost us a lot. Let's put some numbers on it. So that's our goals here, and thank you for your attention.
Thank you, King. Good morning. So I'm going to build upon what Matthew had talked about in his opening statements this morning, as well as the themes that Gavin and Carrie have brought up. So, of course, we can't rely on history, as Carrie was just saying. We can't trust our intuition that our past experience is going to inform the future. Climate models do. We have to rely on the science. We have to rely on the physics. As you may have noticed, and Carrie was just saying, that climate change is already happening. It's already changed. We're already living in a changed climate. It's going to continue to change. Over the last 30 years, it's really changed dramatically. So in particular, heavy precipitation. Those of you in the Northeast, you may have noticed that it's raining heavier than ever before. That is not a misperception. That is fact, okay? One of the things that we did at First Street, Dr. Jung-Ho Kim, our lead hydrologist, had done a study of looking at how has precipitation changed and comparing that against the long-term climatology from NOAA's Atlas 14. And that's the image that you're seeing here behind me, is that those blue areas, you're seeing 50% heavier rainfall in the 100-year event in 1 hour. Okay, in the 1 hour time interval is where we're seeing the largest changes due to climate change. And this is a pattern that you see all across the country. In some places you're getting less intensity of rain, some more, but you're seeing a lot of the higher intensity of rain. The upshot of all this, you have to use this information correctly. If you're going to be projecting flood, you have to take this into account in how you're going to be translating this information into something useful, as Carrie was talking about. So as an example of the kinds of difference between a physics-based model and a statistically based model, because we throw the term model around quite a bit. There's a big difference between the two. What you've been hearing about this morning from Gavin and Carrie is about physics-based models. When you got up this morning and you probably all looked at your phone, looked at your weather app, and you're deciding, hey, is it going to start snowing yet? What do I wear to come over here to the session? You probably pulled up an app like that's here on the right? So this is driven by a physics-based model, these weather forecasts that you've all come to know and to trust. It's useful to you, right? So the National Weather Service cranks on very large computers, $100 million computers, to get you the forecast so you can make these informed decisions with precision in a useful way. Right? Now, I'm going to pick on the Farmer's Almanac here for a second. You could also, instead, you could choose to take a purely statistical climatological approach and get your decision about what you're going to wear today from the Farmer's Almanac. And I would bet you that nobody in this room looked at the Farmer's Almanac before you got dressed to come today. Because it's vague, it gets you in the ballpark, it's not giving you the precision that you need to make good decisions, right? So generally speaking, the more expensive the model, like Gavin was talking about, none of this comes computationally cheap, but as you bring that precision in and you bring the computational power up, you can get more precise and more useful answers. So at First Street, how do we take the kind of inputs that Gavin and Carrie were describing, how do we take that and turn that into a useful product, okay? So in the middle here of this equation, you see these physics-based hazard models, and I apologize for the shallow water equations up here, but it is a physics-based model. The physics-based models are solving that equation for flood in this case. It's solving those equations to tell you when rain falls, where's it going to go, okay? And so it's a very trusted answer. But it depends upon those inputs. And that's where we're really standing on the shoulders of the giants of the scientific community, including Gavin and Carrie up here, because we're using their work as inputs to these physics-based hazard models, which essentially downscale, a term that Gavin talked about, getting it down to a lower resolution, something useful for decision making. We're letting the physics do that downscaling so we come up with a trusted, precise answer. And you end up with the kind of hazard that you see here on the right, in this case for flood. So you can see changes, and you can see the differentiation from house to house, block to block. That's the kind of stuff that we've heard over and over again is what is needed in order to use this climate information. And let me tell you a story, because if you're using physics-based models, you can predict things that have never been seen before. So I live in Asheville, North Carolina. Actually in a little town just outside of Asheville called Fairview, North Carolina, where ABC News was broadcasting from a week in late September. And if you have a little town of 4,000, you do not want to be newsworthy enough to have ABC News come and broadcast from your town. But we were subject to a lot of precipitation that came up from the Gulf of Mexico to the mountains of western North Carolina. And there was an intensity of rainfall that had never been seen before. And so 2 days before the National Weather Service put out their forecast, I was up here in New York at First Street. I called home and told my wife, hey, sorry, honey, this is going to be an utter disaster. And she was like, wait, what do you mean? Nobody's talking like this is going to be a big deal. Everybody's like, say, well, we've had these remnants of hurricanes before. No big deal, we'll ride it out. I said, no. So by taking the intensity forecast and matching it to our probabilistic flood forecast, I could see where in the Asheville area, how deep the flooding was going to be and how severe it was going to be. And so let my wife know, like, hey, this, we're originally from Miami. It's like, this is going to be like a Cat 4 hurricane. Fill up the bathtub full of water, get ready for no power for a month, et cetera, et cetera. She went and told the neighbors and our friends, spread the word. But, and she was fine, and my family was fine. But a lot of places in western North Carolina were not fine, or still not fine. This image that you're seeing here behind me is a place called Chimney Rock near Lake Lure. It's about 3 miles from my house. And yes, the flooding that came through that area just wiped the whole area clean. There's a lot of areas like this in western North Carolina right now, Tennessee, Virginia, West Virginia. But the idea here is that with the right information, can we understand what's about to happen when it's never happened before, right? If you had a statistical model, you're going to be very limited as to what your understanding of when things go outside of the bounds of what has happened in history. In this case, historical rain event, never seen anything like it before, but it is still predictable when you're leaning on a physics-based model. And so that is, that is the punchline here. That is the punchline of Matt's opening comments also too, is that climate risk is predictable. And if it's predictable, we can do something about it. And this is why I'm very optimistic about action on climate change, because we're getting to the point now where we can quantify this risk at a useful level. And if you've got useful information, you can make informed decisions for your business, for your family, for your community, within government. And so Matthew already showed some of the burn perimeters from the LA fires. This is the same probabilistic approach that we've taken. And it's like, and we've had questions like, oh, why did First Street, get these probabilities right? Well, we weren't sure where an ignition would actually happen in this area, but we were sure when an ignition happened, this is what's going to result. Okay? We did that because we created millions of fires, millions of possible fires simulated in the computer for this area, watched each one of them burn across the landscape, and then looked at the sum total and came up with burn probabilities for across this area. So it depends upon the fuels, depends upon the winds, yes, but we took all that into account and we relied on the physics-based model of how wildfire moves across the landscape. So it is discernible, you can get this kind of precision out of physics-based models driven by the best climate inputs from the scientific community, and the risk is predictable. Thank you very much.
All right, thank you all for those fantastic presentations. I think they've set us up to have some really good conversation as a group. So let's jump into the panel-style discussion section. And I have a couple questions for you based off of some of the things you raised in your presentation. We can look in the news every day and see examples of stories of devastation that are happening in many places around the world. A lot of times the science doesn't get the same level of attention. So I'm curious, from where you sit, what are the big stories in climate science right now? And what do you think that story will look like 4 years from now? Gavin, you want to go first since you looked at me?
So I mean, you know, it's obvious what the big story is, right? Things that were esoteric, academic concerns are now very, very real. The link between those global level changes that we've been predicting successfully for decades and the impacts on extremes, extreme rainfall, extreme wildfire, extreme heat, extreme storm surges and sea level rise, the links between these things have become obvious to everybody. And making those links clearer and improving how these things can be predicted going forward is obviously the biggest story. And it will remain the biggest story. Like 4 years is actually a pretty short time when you're talking geologically. So it will remain the same, the big story. It's linking those extremes to the global mean changes and what that means for people on the ground.
My answer to this question, which complements what you just heard from Gavin, is the marriage of two disciplines, if you will, that used to be very, very separate. So you had the whole scientific community engaged in climate change, understanding the physics behind it, understanding what was going on, and making predictions about climate. That's what we do. On the other hand, you had a community of people who assessed natural hazard risks. That was based almost entirely on statistics for a long time. It still is to most. And they were, of course, these communities were aware of each other, but they didn't work together very much. Now they do. And this bridging is a very important development, I would say, even for science. There are a lot more scientists now than there used to be who are really interested in turning our increasing understanding of climate change into actionable quantitative estimates of real risk, hazard risk, okay? This is happening very fast, and it's one of the things I think is behind the very fast evolution, some of it not great for humanity, I might add, but that's because of regulation, fast evolution of the insurance industry. And I think that will lead ultimately to things like regulatory reform and start to really rationalize our approach to dealing with climate risks.
Yeah, and from my experience, you know, so I used to be a NOAA employee back in the until 2020. I left federal service. But one of the things I had done at NOAA was trying to communicate NOAA's climate science and climate results to economists at the U.S. Treasury. And I spent about 1.5 years doing this, and I gotta say, I completely failed. It was very hard to bridge that gap. But after coming to First Street, when we started to create these property-specific risk metrics, and we re-engaged with the U.S. Treasury, those economists were like, oh, now you're onto something. This is the level of information we really needed. And what it did is it opened up a conversation, which is continuing to this day, that's allowing climate science now to bridge that gap to the economists that are doing fascinating research about how climate change is going to be impacting the U.S. economy or American families or American businesses. And so I think we're just starting to see the momentum starting to build. As we as scientists, we have to learn what the economists and others need in order to use the information and data that we have. So it's been great to see the progress over the last couple of years.
Yeah, great. I'm going to build off of that a little more. My job at NOAA involves me having one foot in the science and the other foot in every other part of the world, basically. So I think, Ed, I somehow inherited some of your work without even knowing that. But let's step into that a little bit more. So put yourself in the position of a financial institution or an asset manager. What science, you all sit with your feet in the science world as well. What science would you pay attention to if you were them right now? And you know, what would you prioritize investing in to try and help that, you know, our financial institutions going forward? You want to go first again?
Well, I mean, so I think we've touched on these issues before, but I think, and let me bring out something that one of your pictures showed. You know, you showed the changes in the extreme rainfall statistics, right? Now, those were very large scale. It was like the entirety of the Northwest, right? Those are the kinds of things that the climate models can predict very well. It doesn't require very fine detail or fine resolution to be able to predict that, because it's a very fundamental consequence of having more water vapor in the atmosphere. But the impacts and your vulnerability to those changes in rainfall, right, that requires information at the finest granularity that you can find. And so that combination of those climate impacts, which are large scale, and those vulnerabilities, which are very small scale, right? That is where people need to be paying attention. You don't need small scale climate drivers, you need small scale vulnerability. And so making sure that you're bringing the right granularity of information to the table when somebody's saying, oh, well, here's how the climate is going to change, is I think the number one task that anybody trying to price this out really needs to think about.
I'd just like to amplify on that bit. I think almost everything that we're doing, especially with regard to the future, relies ultimately on the global climate models. And we need to keep putting, and I would say, more resources into that. We're not doing enough in that realm. I don't do global modeling. I'm not speaking in a self-serving way, but absolutely rely on it. We could be doing a lot more. We should put more resources into it. The other strength, I think, of the global community, and not all of my colleagues agree with me about this, I don't know where you stand on, Gavin, is that there's more than one climate model. Mm-hmm. There are quite a few. And this is really important because we don't have a complete understanding of climate. Probably never will, but we are getting better. But from the point of view of risk, it's really, really, really important to quantify the uncertainty. And I think we can do that, and we must do that, so that when it comes down to the level of the financial manager making decisions, no information that we would give them is complete without an honest quantification of the uncertainty that goes along with that. So that's an area that I would pay a special attention to.
And to add to that, I would reference one of Gavin's figures that he showed. Speaking of uncertainty, and this is good news with uncertainty for a manager. If you're looking at the risk and how it's changing and how the uncertainty is changing over the next, say, 10, 20, 30 years, if you look closely at Gavin's chart, over the next 10, 20, 30 years, there is not a lot of difference between the different climate scenarios. They're very close to each other. And in fact, the uncertainties are overlapping, okay? What this tells us as scientists is that it doesn't matter. What we do with carbon over the next 30 years, we're going to have the same physical outcome in this world in 30 years. So you have a high degree of certainty that this change, no matter what we do with carbon policy and other climate action over the next couple of years, the outcomes are going to be very similar in terms of the physical climate risk. So if you're a manager, I would say understand what your climate risk is today, and if you can get that, nailed down, then that trajectory over the next 5, 10, 20, 30 years, you actually can have a lot of confidence in what that is.
Go ahead.
I just want to add a little caveat, just so there's not a misunderstanding. But that's true when it comes to global mean temperature.
Yes.
And when it comes to regional and local things which we care about, the two different models predicting exactly the same future temperature, let's say, will have very different patterns of change in other quantities. So that's why we have to do that. Okay, and something else I was going to say, but I'll put it off.
No problem. I'm going to ask a follow-up question, so maybe we'll come back to you. I was just at our NOAA's Geophysical Fluid Dynamics Laboratory for their big lab review 2 weeks ago. They developed the first ocean-atmosphere coupled model that sort of set forth the world of climate modeling. And now they have a bunch of different models for exactly the reason you were saying of even within one institution, having multiple models is important for advancing the science, but for also communicating the uncertainty. When we talk to a lot of sophisticated climate science users, the uncertainty is almost more interesting than the actual mean average temperature. We're also finding, and have been hearing, that in many cases our models are actually conservative in a lot of areas. And so I'd be curious as to how you're seeing the response to the evolving science and how you're communicating that uncertainty with the work that you do. If there's any advice you have for our audience of how to engage on that uncertainty piece, because it can be a really challenging area to engage with. And as soon as a scientist says, we're not sure, everyone panics, but that's kind of pretty important part of science is saying where we're not sure. So I'd love if you could dive in a little bit more on that uncertainty piece and how it helps to engage in that.
Yeah, I mean, to say not sure, not know, that's definitely something we as scientists are very comfortable with doing. It's not something, talking uncertainty to somebody is not well versed in the discussion of uncertainty. Sometimes it can get pretty confusing. But one of the things that we do to reduce this uncertainty is to use ensembles of models. So groups of models, because they, as Carrie was saying, they may be behaving quite differently in certain regions. As you add more and more members to that ensemble, you get closer and closer to the truth. And the example I often talk about, or because it's something that most people have experience with, is hurricane modeling, but real-time hurricane modeling from the National Hurricane Center. When a storm is approaching the East Coast, and you all have seen on the internet or on TV, you've seen all these different model tracks, and then the forecaster draws a line down the middle and says, well, that's going to be the official forecast down the middle of this, right? That's an attempt by scientists to use multiple models, all of which are solving the same equations, all coming up with slightly different answers, but saying, okay, they're all wrong, but as a group, they're mostly right. And then we're going to take the middle of that distribution, and that's what we're going to use to inform our decisions. That is a valid approach. What excites me about the future, though, too, particularly with a lot of these new AI and machine learning tools coming on, is the number of ensembles that we're going to have in our future ensembles of these climate models potentially could be very, very large. Right now, we deal with dozens of members for ensembles, but we could easily get to a point where we're dealing with hundreds of thousands or millions and that's going to be driving down the uncertainty even more. As a scientist, I get very excited about that.
I'm going to argue with you a little bit there.
Yeah.
I'll make one general point, which is just because we're uncertain about something doesn't mean we don't know other things, right? We know a lot, but we're also uncertain about a lot. And one of the problems is that ensemble approach, just averaging all the models together and hoping that is close to truth, doesn't actually work when there are real uncertainties. Because what happens is that all of those models, they have certain assumptions that they share. And so when you average all of the models, what you're actually doing is you're saying, well, given those shared assumptions, this is what we think is going to happen. But those shared assumptions may be wrong. And so you can have ensemble averages that are significantly biased compared to the real world, particularly when it comes to climate. Now, perhaps not so much with weather, because you're dealing with something that's a little bit more a priori at that point. But for climate, you can't just average all the models and expect that's going to give you the best answer. In practice, it has done. But in the last round of models, it was clear that some of those models were too biased to be included in those averages. And so you had to be a lot more sophisticated in how you put those different ensembles together. And that's tricky, and that's very much a frontier kind of question in climate science. How do you do that in a sensible and useful way? And I think that's still a bit of an open question, but it's not quite as easy as just averaging.
I hope I didn't imply it was easy. Yeah.
No.
But it's a technique we could. Yeah.
There was this thing called model democracy, like one model, one vote, that people used up until the last IPCC report, because in practice it seemed to work well. But as you start to increase the complexity, if you start to increase the different amounts of things that you can do, then that uncertainty spreads too far, and then the real world says, no, some of those models you have to discard, and we can only keep some of those. So model democracy is dead. But
So is real democracy.
I'm not allowed to say that.
So I want to make one sort of addendum to this. The great Danish physicist Niels Bohr said that prediction is very difficult, particularly when it's about the future. And there is more to that statement than most people give it credit for, besides it being funny, and that is that there is such a thing as predicting the present, and I sort of alluded to it in my talk, that the uncertainty, one of the sources of uncertainty for everything that we do is the difference between what we learn from studying the historical statistics of a hazard, like earthquakes or storms, and what the reality is now. I don't imply that it's any different for earthquakes, but for weather, certainly it is. And that uncertainty, that difference is very large compared to some of the uncertainty that we've just been talking about the future. To me, that's the low-hanging fruit. Getting today's risk right, okay? That's an easier, it's hard, but it's an easier task than the future. And it's what most of us base our decisions on. The difference between what science, I think, is prepared to give you and is giving you, and you heard about that earlier today, is beginning to give us, and what we were getting from historical statistics is a huge difference. And there's less uncertainty in that statement than there is about statements about the future. So I hope we can go for that low-hanging fruit first in some ways.
Yeah, and I think it also supports the point that we need to continue to do the observations and monitoring so that we can look back on how these models are performing, and we can see whether or not the advances we're taking, whether the biases or uncertainties we have in the model are actually accurate or not. That's how we test them, right? It's also where we need to invest in targeted research and field campaigns, and so it further supports the need for targeted science as well as continued long-term monitoring and observations from our satellites like those NASA and NOAA operate, but also from our in situ ground-based observations, our weather balloons, our temperature gauges, and so that we can continue to track the progress in these and be able to evolve our communication and know whether one model should get 2 votes versus 1 or whatever Gavin would propose as the solution going forward. So great. Well, I'm gonna switch to a slightly different direction for a minute. My husband doesn't like taking me out to parties anymore because he says, stop talking about work. Everyone finds out I work on this. And then they're like, tell me more, what's gonna happen? So I'm the person that he doesn't want to bring to the party anymore because there's kind of a lot of doom and gloom around climate change and what's happening right now. But I always try and shift to the things we can be optimistic about. So, I've worked my way back into the social circuit. And I'd love to hear, ideas from you all on what we can be optimistic about in the face of what often shows up as doom and gloom in this space. Should we reverse order, Ed? You can go first this time.
Sure. Yeah, if you know me, you know I'm an optimist by nature. But I think we do have a lot of reason to be optimistic with climate change, with the caveat that if we make wrong decisions, it just gets, or we wait too long, things just get more and more expensive. But basically speaking, I'm optimistic because the information that we have from the scientific community, information that we have from what I've been calling the golden age of observations in the last 10 years, we're never going to see something like this great international collaboration and such from NOAA, NASA, the EU, everybody. We have more information than we've ever had before. And it is creating a ability, as we're talking about today, to define risk, to quantify risk. And with any challenge that you have in your life, right, if you've got information about it, good information that you trust, then you can make informed decisions and take action, right? So I'm optimistic because we're there now. We're now on this cusp of saying, yes, we can create these useful information products. We know we have to do some things about climate change. We know we have to protect ourselves against the physical climate risk that is coming. But as opposed to maybe 10, 15 years ago where it was a lot of guesswork, now we've got hard numbers. We're actually quantifying this. We're putting uncertainties on these so we can move the whole ship forward. That makes me very optimistic. Like I said, the speed at which we do this, if we don't do it fast enough, it's just going to become more and more expensive as we go into the future to bring some of these remedies and mitigation strategies to bear on the climate change issue. But it's not like that we're shooting in the dark anymore. We know what we have to do, whether we have the political will or the finances to do it is a different issue.
So I share Ed's optimism. about the future, and let me tell you what the basis of that is. I think the quantification of climate risk, of just getting away from just proselytizing, oh, it's going to be bad, to actually putting numbers on what your insurance rates are likely to do or what's going to happen to your property value, is one of two pillars, I think, of a basis for a whole change in how we're dealing with the risk. The other pillar is what we're going to talk about this afternoon that also has to be in place, is that the society, the whole financial, political environment, has to get to a place where it can respond to those changing signals of risk. That means the regulatory environment. That means rethinking the provision of federal flood insurance. That is rethinking the way we have basically stopped risk signals from getting to the people by overly protecting them from the risk, all right? That's beginning to happen. Insurance rates are going up. It's going to be disruptive, and we're going to have to figure out how to soften the blows. But if we keep subsidizing risk, causing populations to migrate from less risky to more risky places, not all the climate information in the world can change that. So those, in my view, those two things have to happen, but they are happening. So I'm optimistic.
I find it hard to be optimistic. There are some good things happening. The effort that's being put into climate risk is finally commensurate with the size of that risk. That is good news. I mentioned previously that the future trajectory is still within our power to change, right? We as a society, and some of you individually, have agency. And by making different decisions, we can avoid the worst things that are foreseen. If we were to stop emitting carbon dioxide tomorrow, climate change for temperatures would stabilize, right? It would not get any worse. That means that every bit of carbon that we put out, that's what's making it worse, right? So society has agency, and that's a very important thing for people to understand, because other times people think, oh no, we're on some wild runaway train that we cannot affect, but we can affect it. And that's a very, when talking to the public, is a very optimistic message. But, I'm not going to go into the doom and gloom. I am also quite tedious at parties. So
You and I can hang out, Gavin.
we can hang out. But I think those two things are good. And then let me throw in one third thing. We are finally measuring things that we have been trying to measure for many decades and have failed, but we're finally measuring them. And that's the amount of stuff in the air, the pollutants in the air, the aerosols, the smoke particles, the ash, the sulfates. We are finally measuring these things at the level that they need to be measured. And that has been by far the biggest uncertainty in both understanding how things have changed in the past and how things are going to change in the future, or even how things are changing right now. And those new observations are absolutely crucial for improving the models, improving the forecasts, and making more skillful predictions for the future.
So I will come in, though, and say, from my perspective, having worked on adaptation and resilience and climate science domestically as well as around the world, both for NOAA and for the Department of State, and I think there's tremendous innovation going on around the world. I think there's a lot of scientific advances that we never thought were possible. When I got my first federal job in NOAA back in 2009, I remember meeting with groups of scientists, and actually even before that in 2008, 2009, when I was working for the Senate Commerce Committee, we did a hearing on climate modeling and had a long list of impossible problems that we didn't think we could solve: clouds, aerosols, how these things showed up. And the amount of advancements that the scientific community has made on what just, 15, 20 years ago we thought was impossible, I think it gives tremendous hope as to how much our innovation, hard work, the investments that we're making can pay off. I additionally would like to add that I think, we're seeing a lot of economic reports coming out saying that the return on investment of high quality climate information services pays out huge dividends, whether you go with the Global Commission on Adaptation, whether you go with the Boston Consulting Group report, whether you go with the Chamber of Commerce All-State report, you're seeing anywhere from 10 to 1, 9 to 1 returns on investments, 13 to 1 return on investments, sometimes 30 to 1 return on investments, where $1 spent on improving the amount of information you have around climate can help you save resources. It can help you identify the opportunities as well as the challenges. So I'd be curious as to your thoughts about, what investments are needed sort of in the next step to try and get us, what are the impossible problems that we should have on the list right now that hopefully, if we come back here in 15 years, we'll say that this seemed impossible, but we've checked the box. Is there anything you'd like to put on the table, particularly for those of us who are producing the basic science, the basic observations that support groups like you all, and what's your wish list? Do you have like 2 to 3 impossible problems that you think we should be working together to solve? See, I got you smiling, Gavin.
Okay. So let me come back to that previous question, right? So I was, thinking I should be able to say something about the one thing that's wonderful right now is the depth of talent that early career people who are coming into this field are bringing into this area, right? You're seeing a bunch of folks here who've been in the trenches for literally decades, okay? We have risen, like we can speak nicely, we get invited to these things, but we're not doing the work, right? Maybe Ed's doing the work.
No, I'm not.
But the young folk that are coming in knowing that this is a big problem, they are bringing the ideas, they are bringing the energy. And the one thing that they're working on is machine learning. Now, we haven't really discussed that very much here, and I'm sure all of you go, generative AI, oh no, that's terrible. Okay, maybe you'll think it's great. It's terrible. For science, though, machine learning, outside of the generative AI hype, is super useful. It doesn't give you everything. It doesn't tell you what you want to know without a lot of scaffolding from the physics, from the observations, and all of the other things. But it allows us to learn from what we already know. We can create emulators of models that are as good as the models themselves. We're seeing that with weather forecasts. The emulators of weather forecasts are almost as good as the weather forecasts generated from the physics-based models, not quite. But the ability, you mentioned this, to have much, much larger ensembles. Much, much larger ensembles means you're sampling the tail distribution for the weather events at much greater fidelity than you could possibly get with the old style of working. It allows us to build, model spreads that sample all of the uncertainty in ways that we could not have even conceived of doing even 5 years ago. So that is extremely energizing and will make a huge difference going forward. And so if you're going to invest in stuff, invest in that. But leave the generative AI on the side.
Well, I'm conscious of the fact that the best information that we scientists could deliver, even in an impossibly good information, won't do any good if we don't have the means to do something about climate change. And there's where I'm a little bit pessimistic now, because there's a lot of disinformation about what we can do. It's all about energy in the end. People who talk about going, fully renewables often forget that there are 800 million people on this planet with no access to energy at all, which is really remarkable. We hope, for their sake, that changes, and it's projected to change. And by 2050, we're going to be conservatively needing twice as much energy as we need today. To do that, with the kinds of technologies that are available right now, I am pessimistic about. But where the optimism comes in, and this echoes something Gavin said about science, is there's a lot of new young talent in the field of energy and energy production. And so I am guardedly optimistic that we will come up with means of generating energy that are affordable and economic, not to us, not just to us, but to the developing world. And that's so important. If we can't do that, what we do here really doesn't matter. And so developments like carbon capture, not economical today, could be small nuclear reactors, which are really growing in popularity and are clean from a climate standpoint. Those give me some optimism.
Yeah, and taking it back to a U.S.-centric approach, and no, I don't code anymore, but the group, the technical, I was just saying this to somebody last night, the technical group that we've assembled at First Street, I am amazed at their skill level. It is outstanding. It is as sharp a group that I've ever worked with in my career, and very, very proud of that. And then seeing how we can then, going back to something Carrie said earlier too about shielding people from risk, part of that is getting the information out there about what that risk is. And one of the things I would really love to see, and it literally broke my heart in the Asheville example, right? Because many of people I know, some people lost their lives, they lost their homes. Some people are still living in tents in the woods, they still are unhoused. That these people didn't have the information ahead of time, and they were dealing with an antiquated system for flood risk that basically the idea was, well, I'm not in a FEMA flood zone, FEMA designated flood zone, therefore I have no flood risk. I have nothing to worry about. That message cost lives. That message cost homes. And now seeing the entire community, reeling still, businesses going out of business, restaurants closing, because the tourists aren't coming to Asheville anymore, post-event. Seeing these knock-on effects are pretty stark. But when we have the information, and we've got the science is there, and we're putting information out there, but people are still being surprised by the risk they face, right? LA fires, people were surprised, like, oh, we had no idea it was possible to have a fire like this. The science showed that, yes, clearly it was. But the messages often coming through a government agency, a state agency, or a federal agency is not clear enough. We're not communicating that risk clear enough to the populace, to businesses also too, so that this can be understood and take clear action on. And so, like I said, when we know the answer, when we know the risk, and somehow it's not being communicated effectively across our society, it's what a missed opportunity. So I'm not sure if I'm optimistic or pessimistic about that, but since we have and going back to the FEMA, I'm not trying to beat up on FEMA, but it's just the bureaucracy here, right? So those of you that have bought a house know that if you're in a special flood hazard area, you're required to get insurance if you're getting a federally backed mortgage. Okay, great. Well, FEMA did a couple years ago go out and do a full-on different flood study that does take heavy rainfall into account, but the other ones don't. But you have this very absurd situation now where those models that are used only for setting the national flood insurance rates are actually pretty good. They don't include climate change yet, but they're including heavy rainfall, so they're mostly right. And it's like, okay, great. But they're not publishing those maps, right? That information does not go into the definition of a FEMA flood zone. So it's very, very confusing for people, because they're like, I'm outside of FEMA flood zone. They go to get their flood insurance, and this is this huge number, and they're like, well, I'm not going to buy that. I'm not required to buy it, even though it's a clear indication how much risk you have. I'm not required to buy it, so I'm going to forego that insurance. I'm going to expose myself to that risk and put my family and my future income at risk by not taking out of that insurance because I'm not required to have it, even though quantitatively you have a lot of risk. So we have this mismatch out there in the application and the information that's available that I hope we can, as a society, continue to kind of sharpen up so that people at least have the proper information.
Sounds like we all agree that there are some things that go beyond science that would be incredibly useful for making the science as impactful as possible. I'm going to have us end with sort of a rapid fire round response to a question. I will answer it first just to give an example. So the question that I would like you to wrap up with is a quick response to what science or engineering advancement would change everything in this space. And I'm going to pick something really short that I think we actually know how to do, which is improved data management and access systems. The models that we're producing, the observations that are coming in, we have tremendous amounts of data that we can't get out because we're producing it faster then we can release it based on the parameters and systems we have. So for me, I would love for all of the NOAA data that's being produced to be able to get out there for people to use. And we have limitations in the systems that we have. We just can't pass the information on to people who need it as fast. So the data integration and management systems so that many people in this room could use our data to the maximum extent possible. Who wants to?
So yes, what we need is a national scale data analytics facility that is on that is on an unprecedented scale, where all of the data is coming in, all of the observations, all of the models, where people can run the machine learning on top of all of the data there. They can do the process-based analytics that they really need to improve both the models and the predictions. And we don't have that right now. We have publicly available data that is spread across 1,000 different systems that is totally impossible for you to download onto your home system or your company system or anybody's individual system. It sits sometimes in the cloud, but that's not a solution, nor is it complete. And right now it exists by charity from Amazon. That's not a viable, sustainable way forward. The Europeans are building such a thing. It's called the Destiny Data Lake. It will not be accessible to Americans, right? And we need to do that same thing here. There is a data analytics gap that is opening up that we really need to fix. And that allows for an enormous amount of innovation and knowledge discovery and accessibility.
In brief, I would say two things. We in the scientific community, we could change the world by much better job of quantifying and communicating the actual risks of climate change. And if the whole political regulatory environment changed so that, broadly speaking, premiums actually reflected that risk, the world would change. That's how I see it.
And I think to integrate all of these observations into a tool that can answer the questions that we have as fast as we can ask them is, I think, it was just like a blue sky goal years ago, but now with the advent of foundation models in the AI world, we're starting to see this actually start to happen. And Gavin mentioned the remarkable progress, particularly over the last 2 years, in AI weather models. But there are people right now that are working on those models that have been made public. Were trained off of model results, not off the observations themselves. But there's groups of people that are now working on training those models from the observations themselves. So conceptually, you can imagine taking all these observations and bringing them together, bringing them into this foundation model, and so that the analysis can be done much more simply because you don't have to worry about formats, whatever. You need to be able to ask the right question. This, again, like everything else, I make it sound easy, and none of this is easy. But the technology, it's very exciting to see the technology get to the point where we could really start to unlock this incredible wealth of information that we have in a way that you don't have to be a PhD physicist in order to actually use this information. You can ask other questions and discern other things from this mass of observations and learnings that we have and get the answers you need to the questions you have.
Excellent. Well, thank you all for the incredible insights you've provided today. It's really a privilege to be able to have all of us sit in front of you all, and I hope that we'll have continued discussions throughout the day to follow up on topics of interest. This is a start to a conversation, by no means the end of it. So.